There's often a hard way to do a problem and an easy way. When you utilize the symmetries of a system, it often makes the problem easier, and the hydrogen atom is a good example of a system with various symmetries. We model the hydrogen atom as an electron bound to the nucleus by the Coulomb force. Constants of this system's classical motion yield physical observables that allow us to label the states. In particular, the allowed energies are labeled by the principal quantum number n. The allowed values of the angular momentum, the total angular momentum, are labeled by the orbital quantum number L. And allowed values of the electron's z component of angular momentum are labeled by the magnetic quantum number ML. Consider the following problem. Calculate the average potential and kinetic energies for the electron in the ground state of hydrogen. Calculate the uncertainty product delta R delta P for the 1s electron of a hydrogen atom. Compare the probability that a 2s electron of hydrogen will be found within a radius of R equals 4 a naught with that for a 1s electron. We'll start with part 1. The ground state of hydrogen is the n equals 1, L equals 0 state, and I've written the probability distribution here, and it has an energy of minus 13.6 eV. So the electron is bound by the Coulomb force to the nucleus, so the potential energy of the electron U of R is just the Coulomb potential, minus K E squared over R. We can calculate the average potential energy in the 1s state. So the average potential energy in the 1s state is given by the expectation value integral from 0 to infinity of U of R integrated against the probability density, P1s of R, dr, 0 to infinity because R runs from 0 to infinity. So I'm not going to do many of the integrals in this problem on the board, but most of them are of the form, since we're going to have a factor out here that goes something like R, P has an e to the minus R factor. So most of these integrals are of the form integral 0 to infinity x to the n minus 1 e to the minus x. And this equals dx. N minus 1 factorial. And so this is a useful integral to know in doing the integrals in this problem. But for all of the details, I go step by step in the attached PDF to this video. Okay, so doing the integral, what we would find is that the average potential energy is minus 27.2 eV. Now, we can get the average kinetic energy just by relating it to the total energy, the average total energy in the 1s state. This is just E1, minus 13.6 eV, which is equal to the average potential energy plus the average kinetic energy. And so, plugging in, we could solve for the average kinetic energy, K, in the ground state of hydrogen equals a positive 13.6 eV. And this is positive like we'd expect a kinetic energy to be. Okay, so let's move on to part 2. In part 2, we want to compute the uncertainties delta R, which, remember, is given by the expectation value of R squared minus the expectation value of R squared, square rooted, and same thing for delta P. Delta P equals root expectation value of P squared minus expectation value of P squared. And we want to compute these in the ground state. So we're going to have to do some integrals. The expectation value of R in the ground state is given by integrating R against the radial probability density, P1s of R, dr. And again, this integral is going to turn out to be of this form, and the details are in the attached PDF. The answer turns out to be 3/2 a naught. Remember, a naught is the Bohr radius. So the important thing to note about this relation is that it's not the Bohr radius, which we know is the most likely place the electron will be found. It's actually a little bigger than the Bohr radius, and this is because this probability distribution is asymmetric about its peak. So we would do the same thing for r squared, just with an r squared rather than an r in this integral. And what we would find is that the average value of r squared for the ground state is 3 a naught squared. And so finally, plugging both of these into the uncertainty delta r, what we would find is delta r equals 0.87 a naught. And this uncertainty delta r is telling us about the spread of the peak in this probability distribution, essentially. Now, by symmetry, the average value of the momentum of the electron is 0. And we would just need to compute the average value of p squared. But this we can get from our calculation over here. We already know what the expectation value of k is. And of course, the kinetic energy is p squared over 2m. So the average value of p squared is just related to this answer we already got over here. And so we can do that algebra, plug in here, and at the end of the day, what we'll find, putting this all together, I'll write it over here, is delta r, delta p equals 0.87 h bar. And this is our answer for part 2. And the thing to note here is that we've indeed gotten an answer that's consistent with the uncertainty principle. For part 3, I've drawn a plot of the probability densities over here to help us visualize what's going on. We can compute the probability that the electron in either of these states will be within a radius of 4 a naught. So we'll call that P1s, that the electron is within 4 a naught. And for the ground state, this is the integral of the appropriate probability density, P1s of r dr, from 0 to 4 a naught. So this integral requires integrating by parts a few times, and see the attached PDF for the full details. The answer for the ground state is 0.99. So the point is, the electron has a 99% chance in the ground state of being found within a radius of 4 a naught, meaning most of its probability distribution, it happens before 4 a naught. This makes sense. We already know that the most probable place the electron will be found is at a naught. The average place it will be found is at 3/2 a naught. And there's only the single peak in this distribution. For the 2s state, P, we can calculate the probability, again, by integrating the probability, the appropriate probability density. So this is given by integral from 0 to 4 a naught of P2s, which again I've written right here. And again, this integral requires integrating by parts a few times. The answer is 0.18, so an 18% chance that the electron will be found before 4 a naught, which reflects the fact that most of the probability is, most of this probability distribution actually happens after 4 a naught. There's actually going to be a second peak in this red line at around 5 a naught. Let's get a different view on these results. I've plotted a different view on these results here. The darker colors correspond to places the electron is more likely to be found, and the lighter colors to places the electron is less likely to be found. In the 1s diagram, the dark ring at r equals a naught corresponds to the peak of our blue line probability distribution here. Meanwhile, for the 2s state, there's a white ring at r equals 2 a naught, corresponding to the minimum of our red line in the probability distribution here. It's a ring of zero probability. The electron has zero probability of being found at r equals 2a naught in the 2s state. The fact that this diagram is getting darker and darker at larger radii corresponds to the fact that the electron is more and more likely to be found further from the nucleus. Both of these states are spherically symmetric, but what we've learned is that the electron is much more likely to be found further from the nucleus for the 2s state.